Okay, so thanks a lot to organizers for inviting me to deliver talk here. It is clear from the title of my communication that I want to compare two quantum objects, reflection equation algebra and quantum group. It is done, this work is done with Saponov. Now his student Mikhail Zaitsev contributed a lot. And finally, I want to begin with the classical, I mean, Poisson level. In Poisson level, you know well, there exists the so-called Sklenin bracket, Poisson bracket. So with bracket is defined as follows. So we consider A matrix, classical A matrix, which is defined the usual way as follows. Finally, we assume that the generators are normalized in the usual way. And finally, after that, we introduce the Sklenin bracket as follows. So it is just application of A by left on the left-hand side and minus the same but on the right-hand side. And finally, we have the following property for a particular case of A series. So for G equal to SLN. In this situation, it's possible to cancel condition determinant equal to 1, and finally to get a Poisson bracket which is well defined in the enveloping space, vector space. I denote with the corresponding Poisson bracket Sklenin, but now it is defined in the on the linear space, vector space. Okay, so now Sklenin bracket is well defined in the symmetric algebra of GLN, and it possesses the following property. If we have if we have two functions such that they belong to the center, Poisson center, of course, of the linear GLN bracket, we have that they commute in sense of this Sklenin bracket. And as it is a very important property for constructing integrable system. But as example of such functions, we can take trace of t in power k, where t is composed from the generators t, y, j, satisfying the usual GLN bracket. But it is very necessary to emphasize that the bracket Sklenin and the usual linear bracket GLN are not compatible. So instead, the bracket Sklenin introduced above is compatible with this linearization, which is called the first Sklenin bracket. Okay, but at the same time, when with studies we developed, finally I was interested in the following problem. I consider A bivector belonging to G in power 2. G is any simple algebra, and if we apply this bivector with add action to two functions, after that multiply with sign means the product, so whether this bracket is Poisson or not. So with this Poisson only if. So it is a sufficient condition. If R is Q-symmetric and satisfies the classical Yang-Baxter equation presented here. So in this situation, it's very easy to see that it is Poisson bracket, nothing more. And as such example of such R, we can take H product with X in the situation when we are in SL2. But it is not so interesting because such a construction cannot come from quantum group. So how it's possible to quantize the Poisson structure presented above. So if we quantize R, small r, we have large R, which is operator acting in the space V in power 2, satisfying the, I prefer to call this relation braid relation. It is more or less that quantum Yang-Baxter equation, but it is involutive. So R squared is equal to identity. And this is the reason why it is not come from a quantum group. But nevertheless, I introduced a braided version of Lie algebra GLN. So it's possible to extend R on space of endomorphism of V. And after that, it's possible to introduce a new bracket, which is X tensor Y minus we transpose them by using extension of R. What is way to extend R as follows to R as follows. It is a delicate question. I don't discuss it here, but finally we extend and we get R curved. And finally we have now the structure which is a braided, I call it braided or generalized Lie algebra. But in this construction, R as follows is also involutive braided. Okay, now, sorry. So now, fortunately, if G as SLN, so if G belongs to A series, the bracket introduced above by myself can be slightly modified. At once we can get after quantization an algebra related to quantum group UQSLN. How it's possible to do? The situation is as follows. If we consider G, which is equal to SLN, and if we decompose the space G in power 2 on irreducible G models, the component G itself comes twice. Once in symmetric part, second component of symmetric part, and once in skew-symmetric part. And by considering a properly normalized SL covariant map from symmetric part to skew-symmetric part, we can add with alpha to the above Poisson bracket and to get to above bracket, which is not Poisson. And in this way, it's possible to get a Poisson bracket which is well defined on the space symmetric part of GLN. So Poisson bracket, which is finally constructed in this way, is denoted as follows, reflection equation, because reflection equation is just a quantum analog which we get after quantization of the above bracket. Now, why it is not possible to do the same thing for other simple algebras? Because in the decomposition of G in squared onto in irreducible component, G itself comes once. And finally, it is not possible to construct an analog of alpha. So this is the reason we are dealing only with A series. So I want to emphasize that the bracket which correspond to reflection equation and that linear bracket GLN are compatible. So any combination, linear combination of the bracket is Poisson bracket. What is simultaneous quantization of this Poisson bracket? It is just a reflection equation algebra, but I call this modified because reflection equation algebra which is not modified, it is defined by the left-hand side, which is equal to 0. But here we have second-degree elements, and here we have linear elements. So I call it call this algebra modified reflection equation algebra. But it's necessary to say that modified reflection equation algebra and non-modified reflection equation algebra are isomorphic to each other. Okay, finally, now we have two quantum objects. This quantum object arise from quantization of the above bracket, and the quantum objects are as follows. If we quantize the Sklenin bracket, we have the so-called RTT algebras. RTT algebras are presented by the following relation, where T is the matrix generated by formal generators. We put here, and we have a family of relation on generators. And reflection equation algebra is as follows. You see, we have here L1, L1, here T1, T2. So it is not same. Why it is not here L2? It's possible to present this algebra in another form with L2, but I prefer with one. Finally, the both algebra are unital, so we have units in both, and the Braden are entering in definition of the both algebra it meets the Hecke condition. So the second equation as follows. We assume Q to be generic, so Q analog of any number, any integer is not 0, and I would like to say that many years ago I constructed a lot of Hecke symmetries. I call as follows Hecke symmetries, which are necessarily related to a Lie algebra. So without any Lie algebra, it's possible to have the corresponding Hecke symmetry. But for R constructed by myself, it's possible to denote the corresponding algebra, RTT algebra and reflection equation algebra. I denote them as follows, and finally they are presented by the same formula. If R comes from the quantum group of series A, it will be called standard. Okay, now, in both algebras, it is possible to define quantum determinant, Q determinant of T and Q determinant of L. In the algebra L on R, of R, in the reflection algebra, the quantum determinants are central, always are central. In the RTT algebra, its centrality depends on R. For some R it is so, for some R it is not so. And if R is standard, if it comes from the quantum group, in the RTT algebra it is central. If we want to speak about quantum group itself, it's necessary to define first the factor RTT algebra over the ideal generated by determinant is equal to 1. After that, to pass to Hopf dual. This algebra is Hopf, and so the Hopf dual is well defined. But they exist are metrics with big R, which are not standard, of course, even for deformation case. For instance, they exist the so-called Kramer-Gervais matrix. It is a Hecke symmetry because it is just subject to Hecke relation. It is also deformation of the enveloping algebra, similar to standard case, but I want to say that if we consider reflection equation algebra, it is deformation of the enveloping algebra UGLN. And if we consider quantum group, it is not a deformation of algebraic structure. It is deformation only of co-algebraic structure. So this is the difference between two cases. And now, there exists a construction for which describes the center of the quantum groups. This construction was presented in the paper by Reshetykhin and Tajan Fadeev in Leningrad Mathematical Journal. And finally, they are defined two matrices, T plus, T minus, and composite, these matrices are composite from elements of the quantum groups. And finally, these matrices are subject to the following RTT type relations. So we have this relation for each of them, and this is mixed relation. You see here T plus, here T minus. And finally, one condition more, some relation on the diagonal is imposed. So we have that matrices are equal to each other on the diagonal. And if we introduce the matrix L as follows, T plus divided by T minus divided means that we apply to this matrix antipode, which is well defined. When according to Reshetykhin and Tajan Fadeev, the elements trace, but Q trace, it is not the usual trace, of L in power K. The matrix L is defined as follows, and these elements belongs to the center of the quantum groups. So it is just the central result, as you wish, construction Reshetykhin and Tajan Fadeev, but in the paper it is done for other algebras as well. So by this construction, finally, it is possible to map the reflection equation algebra in the quantum group. And finally, if we know representation theory and quantum group, but with map, we can construct representation theory of reflection equation algebra. But first, it is not unique. It's possible to construct the matrix L in another way. So in this situation, we have another embedding of reflection equation in quantum group. Moreover, this construction is valid only for standard case. So only in situation which R is standard, the quantum matrix R. Now, here I want to stress once more that Q analog of tracer, it is not usual tracer. It is just a usual tracer, but the matrix A, it's necessary to multiply it by another matrix, which depends on R, or on the initial matrix. In the standard case, CQ is diagonal matrix. It is Q in power, and so on and so on. And finally, in dimension 2, the simplest example is as follows. However, for my exotic examples, which are not related to any Lie algebra, initial Lie algebra, it is possible to have here non-diagonal matrix. I do not know with matrix CR, because it depends on R. Classification of all possible CR, it is equivalent to classification of the all Hecke symmetries. It is a very difficult problem. And now, realization of quantum group via RTT relation following the paper of Reshetykhin and Tajan Fadeev was used by in the papers, 2 or 3 papers by Molev and Koff and Toll, eigenvalues of quantum Gelfand invariant and Q immanent and high Capelli identity, but Gelfand invariance, the offer means the element as follows. Finally, we use for this element another terminology. We call them power sums, but it is the same. Finally, the Molev and Kolfos, they study only the standard case because they use construction of Reshetikhin and Takhtajan-Fadeev, which is valid in the standard case only. But by computing the value of trace of L in power k and different representation, they obtained I mean Molev and all, the analog of Perelomov-Popov formula. What does it mean Perelomov-Popov formula? It says that in irreducible model V lambda labeled by the partition lambda, where all components are non-negative integer, the quantity trace of L in power k in situation when L is generated matrix of the usual enveloping algebra GLN in this situation. And in this case, this quantity became scalar operator, and Perelomov and Popov computed with scalar operator. So it is just presented by the following formula. As you wish, it's possible to call it character. Okay, now I would like to say that there exists another approach developed by myself and my colleagues, Saponov and Pyatov, and finally, if R is even, or I call this situation also GLN type Hecke-symmetry. It means that it looks like bosonic situation, so we have no fermion. If we have even situation without fermion, reflection equation algebra is subject to Cayley-Hamilton identity. It means that we take the generating matrix of this algebra and they exist a polynomial as follows, such that if we put here with matrix L, we have 0. And moreover, very important property, the coefficients of this polynomial are central in this algebra. So in this situation, it's very natural to introduce a central extension completion of this algebra. So we introduce the roots or eigenvalues of the matrix L in the natural way as follows. And finally now, instead of the algebra, reflection equation algebra, we can consider reflection equation algebra completed with mu, with eigenvalues. Now, in this situation, in previous situation, the leading coefficient is assumed to be 1, a leading coefficient here in this polynomial. If we consider non-even case, so if fermion or something looking like fermion are allowed, so for example, if I deformational superflip, then K, it is just the degree of this polynomial. In this situation, K is equal to m plus n, and in this case, the leading coefficient of this polynomial is not number. In this case, it's necessary to introduce two families of eigenvalues, mu and nu. And finally, we consider now the algebra, reflection equation algebra, extended with mu and nu, and I would like to say that the fact that we have a non-commutative algebra and generating matrix in some sense of this algebra is subject to a polynomial relation, a coefficient of this polynomial relation are central, is very, very rare. So it is not many algebras known on possessing this property. So it is only known for some enveloping algebra of usually algebra. It is also valid for reflection equation algebra, and it is valid for the quantum groups, but for quantum groups UQ, it is valid only by the fact that it's possible to embed reflection equation algebra in quantum group for this reason. Okay, now if we have, we introduced two family, if fermions are allowed, so if we have two family, mu and nu, and we would like to express all central elements via mu and u, via eigenvalues. And this formula is formula analog of the Popov-Perelomov formula, but in U situation, which is not even, which is not where fermions are allowed. So, and now the following three questions arise. The first question: how it's possible to construct representation, irreducible representation of the reflection equation algebra? In the standard situation, it is not difficult by using construction of Leningrad mathematical school, but it is not so in general. What are value of quantity mu and u? It's with irreducible models. And what is analog of the trace? For more general, for which algebra it's necessary to introduce a generalized trace? For which algebra the usual trace is not sufficient. So, for example, if you are dealing with superalgebra, it's necessary to use supertrace. Here, similar situation, but in much more general setting. Now, recently, Mikhail Zaitsev, it is just upon a student, have computed the value of mu in this model, in irreducible model, but only in the situation when R is even. So the case when R is not even is more difficult, it is not yet computed. And finally, by using this, it's possible to express characters of any central element, for example, for power sums, Gelfand element as you prefer. Character of Schur polynomial is possible to compute that. And I would like to say that Molev and all, they computed this quantity and obtained the same result in concrete, in particular situation when R is standard. So we are dealing with standard situation, we are dealing with general situation. And I would like to say that the methods are not similar. If you dealing with general situation, it's necessary to apply a matrix technique. We introduce this term for many formula which are valid for any Hecke symmetry. And in this situation, standard situation, it is possible to use the method proposed by Leningrad Mathematical School. So the methods are different. And now I want to compare the properties of RTT algebra and reflection equation R. For example, what is center of reflection equation algebra? And what is center of RTT algebra? In the reflection equation algebra, the center is more or less similar to the center of enveloping algebra. And if R is even. If not, if it is not even, so it looks like the center of this algebra, superalgebra. And in the RTT algebra, the center is very poor. So it contains only determinant of T for some R, and for other R it is not so. But now they exist But in this algebra, in IITP algebra, there exists a commutative subalgebra, we call it beta, of course, which is generated by the following element. We take T1, T2, and so on. Finally, it is just the generated matrix, but pushed on the second position, on the third position, and so on and so on. After that, we multiply here by any polynomial, any polynomial in the R1, and so on. And we apply trace, but of course, trace which depends of R for the moment. But in the reflection equation algebra, if we use a similar formula, we get the, no, here it is not center, it is the beta subalgebra. So with this way, to construct a beta subalgebra in the IITP algebra. And in the reflection equation algebra, it is a central element. They are central element. We have more or less similar formula, but you see now instead of L2, L1 overlined, it is L1 without overlining. So, but L2 is L1, and here we put R, and here we put R minus 1. So the difference is from the first position on the second position to the third position and so on, it's necessary to push the matrix R by using to push forward the matrix L, it's necessary to use R. It is very important property. If you consider the super cases, super algebra, it is similar. So here it's necessary put instead of R, super transposition. Okay, but now what I want to say? I want to say that in IITP algebra, it's possible to use instead of the R trace, the usual trace. So here, if we erase R, it is also valid. So it's possible to construct beta subalgebra by using the usual trace. And the proof is here. It's very easy to see that what is R trace? R trace, it is the usual trace, but here we put a special matrix. C1, C2, why C1, C2? Because we have here K position. And now I denote Cy multiplied times Ty by T nu, tilde. And I would like to say, it's finally, it is demonstration, that for T tilde, the relation of T tilde 1 and T tilde 2 is similar as initial relation in IITP algebra because of the following relation on the matrix C, C1, C2. So I would like to say, if C are constructed adapted to R matrix R, so we have here R, C constructed following the initial Hecke symmetry, so the following relation is always valid. But for reflection equation algebra, it's absolutely necessary to work with R traces. It is not possible to use the usual trace. Okay, now, what are the discrepancies of this algebra? So, for example, reflection equation algebra can be equipped with a joint action of the quantum group, but IITP algebra cannot. Of course, I speak here of the standard case. The IITP algebra can be equipped with a bialgebra structure, but reflection equation algebra can be equipped with braided bialgebra structure. I don't want to discuss this notion. But in the reflection equation algebra, it's possible to introduce analog of partial derivatives in the generator, and thus to introduce analog of Weygothenburg algebra. For example, here, I present here, maybe it looks like, what is problem? No, it is here.
What is your presentation here? No.
On the left? It's gone.
IGS.
Where is it?
Yes. Yeah.
This one?
Yes. But it is under the screen under.
Thanks. Okay. So you see, here we introduced an analog of algebra. What algebra? Analog of Weil-Heisenberg algebra. So it is just a definition of the initial algebra. It is similar definition for partial derivative algebra, but you see the R is replaced by R in minus 1. And the relation between two generating metrics are as follows. So how it's possible to guess with formulas? I don't know how it's possible to do. Finally, we checked that this definition is good. And you see entries of the matrix D plays the role of partial derivative in the generator of the initial matrix. Finally, here I present only the classical example. The classical example means that we consider R, which is equal to the usual flip, P, it is the usual flip, and how it's possible to define the matrix L and D. So it is very natural. L is A, B, C, D. D is just partial derivatives, but you see here B and D are transposed. And finally, the statement, which is very easy to verify, that L multiplied by D, it is matrix satisfying the following relation. This relation is a relation of the enveloping algebra U, G, ln 2. And so in this situation, we can see that elements of this algebra are presented by vector fields. And now, in our current case, Q setting, we have more or less similar situation. If we consider the algebra introduced one page above, we have the generating matrix of reflection equation algebra, a matrix generated by partial derivatives, and statement is the matrix which is product of two matrices satisfies the modified reflection equation relation. So it was very surprising for us, but you see that in this Q case, in quantum case, with relation is valid for any R, without any restriction. The only restriction is for R, the corresponding trace R can be defined. It is only requirement. Okay, what is Capelli identity? Capelli identity is as follows. In the classical case, if we consider product of L and D, I denote with matrix now L hat, we have the following relation. You see, it is more or less a statement that determinant of product two matrix is product of the determinant. But now the product of two matrices is not commutative, with this reason why it's necessary to define the left-hand side more with precaution. So you have here L hat displaced a little bit. Here K is diagonal matrix, and with determinant is so-called row determinant. It's possible to present with also with column determinant, and it's possible to present with relation in the following matrix form. But I don't want to go into detail. So now, what is an L in Q situation? An L in Q situation is as follows. With relation was obtained by myself and Saponov maybe 3 or 4 years ago, and I would like to say that with relation is Q analog of classical setting. In classical setting, similar relation was obtained by Okunkov. Okunkov finally introduced the higher Capelli identity, and they are based on the notion of immanence. So now I want to say a few words about that. Here I describe what is Hecke algebra. It is more or less well known. Here the relation of generators. Now, what is property of Hecke algebra for generic Q? It is isomorphic to matrix L, product of a few matrix algebras. And finally, it is semi-simple. And by using this stuff, it's possible to introduce also, it's possible to introduce introduce the so-called Euclid-Murphy elements. Euclid-Murphy elements are introduced in the paper by Okunkov and Vershik, you know, with paper is published in book. And finally, here, Euclid-Murphy elements are defined as well. They are defined in another way, compared with the case on the group algebra of symmetric group. But for Euclid-Murphy elements, it is known that they form a maximal commutative subalgebra in Hecke algebra. And moreover, the center of Hecke algebra consists of all symmetric polynomial in the Euclid-Murphy elements. Now, elements of Euclid-Murphy possess the following property, but I skip this part. So the elements E, Y, Y, lambda, it is element belonging to Hecke algebras, and they correspond to the composition of this algebra in the simple component. Finally, we have the following, we call this quantum universal matrix Capelli identity. I guess, I think that it is most possible form of Capelli identity. You see, because here we don't apply trace, no trace here. So for this reason, we call this situation matrix Capelli identity. Here, J are Euclid-Murphy elements, and they are here image of Euclid-Murphy element belonging to Hecke algebra, and here we have corresponding matrix. Okay, and now it is corollary obtained by Molev and al. So the left-hand part of so it is definition of quantum immanent. This definition was introduced by Molev and Kolfos, but they introduced the situation only for special case, for classic, for standard R. We propose the same formula in general. Okay, so now I want Finally, I have to stop here, or I have 3 minutes? 2 minutes. Okay. Finally, the question, the next question is how it's possible to apply more or less reflection equation to construct some integrable models. And recently here, Talalayev came, and finally he tried to generalize by using reflection equation algebra the paper by Deft, I don't know, and Korfer, which is called the full symmetric Toda system. And finally, it is what initiated by the following question: whether by using the stuff of quasi-determinant by Gelfand and Retach is possible to, you know that in the stuff of quasi-determinant is possible to show for a standard that determinant in the RTT algebra can be constructed via quasi-determinant by Gelfand-Retach. And they posed the question, Talalayev, whether it's possible to use reflection equation algebra for this stuff. And finally, he succeeded to show that in dimension 3 it's possible to do. And finally, if we follow the second diagonal of this matrix and we consider 3 quasi-determinant, we have here 3 elements which commute all together, and their product is equal to determinant. So, as you wish, it is application of reflection equation algebra in order to construct few analog of Toda situation, Toda lattice, but it is done only for dimension 3. And I asked recently, maybe a week ago, what is progress, Talalayev. Finally, for the moment, no progress, only for dimension 3 it is done. And the last question, you see, if you have a Poisson bracket, you want to quantize it. It's normally one looks for the simplest coordinate, for example, Darboux system coordinates or cluster algebra, something like that. After that, one quantizes the algebra by using this simplest coordinate system. But I present here another way on quantizing. You see, if we consider the following bracket, this bracket is quadratic because it looks like the usual linear bracket but multiplied by h. In this situation, it's possible to quantize with Poisson bracket as a reflection equation algebra over trace. That's all. So we kill the trace and we have quantization. The question is, what algebra needed introducing the new trace, non-classical trace. For example, if we consider a small generalization of this bracket, here you see h squared, and so on. So it's not difficult to see that with bracket is Poisson, but how it's possible to quantize it by using the same scheme, I don't know. Finally, whether it's possible to do with the usual trace, or maybe it's necessary to introduce something like the unusual, quantum trace. I don't know the answer to this question, but for me, this question is very, very important from all mathematics, as you wish. But it is open problem. You are welcome.
Thank you.
Maybe one question, then other question is coffee break.
The second presentation today will be given by Fogg. You will be speaking.
Both the same subject. Yeah. Okay. So then coffee break. until 4th.